What's going on, everybody? It's Mr. Gustin. I'm back in the physics conference room today. We're talking about magnetic flux. We've been talking about magnetic fields and the right-hand rule and how magnetic fields, when they're near a current, can produce these perpendicular forces and whatnot. But now we're going to start talking about induction using magnetic fields and things like that. Producing currents using changing magnetic fields and whatnot. But the first thing we got to talk about is magnetic flux. And flux is a fancy name. It's like a sci-fi word that comes up. But basically, it's defined as this. It's the amount of a magnetic field that exists through a loop of wire. That's it. It's a measurement of that, okay? Here's the basic equation for it. We see that the magnetic flux, phi, is equal to the magnetic field times the area of that wire taking up times cosine theta. And so when we think about this cosine theta idea, like to maximize cosine theta, we want something to be parallel, right? If we think about our equations from the past, we think about the work equation, which is FD cosine theta. If the force you apply and the direction you are moving in are the same direction or parallel, you get a maximum amount of work done on that object. If there's a difference angle, if it's at 90 degrees, right, if it's your force is applied upward, but you are trying to move it perpendicular to that or at 90 degrees, you're going to get no work done. So anytime you see cosine theta, what you're really looking for is the parallel components of these two things. So what does that mean, though? Because I understand how a magnetic field can possibly have a direction. If I have this little sample here, this is a bunch of straws. Clearly, the magnetic field is in this vertical direction. But if I have this hoop to represent area or a loop of wire, it's weird to think about direction of area. So let's first talk about flux. What is flux? Flux is the amount of magnetic field going through a loop. So if this is a loop of wire, you can see the B field going through that loop. This is the amount of flux. The number of little straws I have here going through it, that would be flux. And if I moved it over this way, I'd have less flux because I'd have less of the magnetic field through it. Now, the other thing we can talk about is not just how much of it, but the orientation of my loop. If my loop goes perfectly up like this, there's actually no straws going through it. So my magnetic field going through this loop or area of wire is zero. So now we're starting to get a picture of what might this direction be for area. Let's look at an example, right? So if I have my B field going up like this and my loop of wire like this, we would say that's a maximum amount of flux. Here's how we can think about this. This is basically saying that, like, if this cross-sectional area is my loop of wire, that is my area, the vector, the direction of area, is perpendicular to its plane. So if this is the plane of the loop, or if this is the plane of the loop, the direction of it is up. And if I see my direction of the area being up, well, notice that's the same direction as my magnetic field. So the area is also pointed up. This angle between area and the B field is 0 or 180 degrees. This is the maximum flux that I have here. The opposite of that would be this. If here's my magnetic field and here's my loop of wire, and we think about it this way, what's the angle between my loop of wire and the magnetic field? Well, this is 90 degrees, and that's why none of these lines go through it. My flux would be 0 here. Okay, so magnetic flux is just, by definition, the amount of B field through a loop of wire. Its equation is this. Now we talked about the direction of the area vector. Let's try one example problem here I've got on the board. I've got this loop of wire. This loop of wire is 40 centimeters long, 20 centimeters high. I've got two different magnetic fields going into it. So if I want to find the total flux, I'm going to need the flux from the inward magnetic field and the flux. So I guess plus or minus, because they're in opposite directions. This is into the page, this is out of the page. Minus the flux from the out of the page magnetic field. Let's go ahead and total this up. The total is equal to, well, the B into the page times the area minus the B out of the page times that area. What's the B into the page? That would be, it says in my picture, 2.0. What's the area? Well, my area needs to be in square meters, not in square centimeters, so we got to convert that. This is 0.2 meters squared minus this 1.0 times the same area. I go ahead and I solve these, subtract them, and what I end up with is the total flux for this is equal to 0.04, what is it? Tesla meters squared, right? The amount of magnetic field in an area. Now, I could ask this a bunch of different ways, and there's a couple more practice problems in your packet where I ask you to do a couple different calculations using flux with either no B field or half B field or some B field. Right now, we're just talking about the definition of flux, not changing flux. We're not doing any kind of changing or sliding or rotating. We're just talking about what the definition of flux is, okay? If you have questions, drop a comment, send me an email, ask me in class, all right? Till next time, see ya.